My name is Michael Emanuel, founder and CEO of Adiabatic Materials. Our company is a technology spinout of research done by the ASES group at Harvard, where we've discovered a cheaper and cleaner way to produce hydrogen peroxide. The incumbent production method is a dirty and expensive thermocatalytic process requiring high temperatures and natural gas that is typically obtained by partial combustion of natural gas. We've developed a novel, patent-protected electrochemical process that requires only water and cheap, clean, renewable electricity. Our four founders have diverse scientific and academic backgrounds. I had a 17-year finance career before returning to graduate school and completed my PhD just last week. My goal in changing careers was to make a tangible, positive contribution to the world, ideally at the intersection of science and business. I am joined by three co-founders on the Harvard faculty, Mike Aziz, Zach Schiffer, and Richard Liu. Mike's group has a focus on electrochemical engineering for energy and the environment. Mike is a legend in the flow battery community and pioneered the development of aqueous organic materials for energy storage and carbon management. He was previously area chair in materials science at SEAS. Zach's research group is focused on developing sustainable routes for chemical processes, especially using renewable electricity to drive electrochemical systems. Richard's group concentrates on the development of catalysts and synthetic methods to access complex molecules. Recent work in the Liu group on redox active organic molecules as catalysts for selective nitroreduction reactions has promising applications for the pharmaceutical industry. Hydrogen peroxide is an important industrial chemical with an annual market of $3.3 billion a year. It's also a powerful green oxidizing agent, opening up opportunities to produce other chemicals including caprolactam and epoxides. These additional compounds increase our addressable market size to over $70 billion a year. Our technology breakthrough is an interfacial hydrogen atom transfer process. Research on quinones for energy storage has already led to one successful spinout called Quino Energy. Recently, we discovered an unexpected application of electroactive quinones. After a water-soluble quinone is reduced to its high-energy form, called the hydroquinone, it can selectively transfer an entire hydrogen atom to an organic, water-insoluble quinone. This allows us to replace heat with electricity as the driving force for the desired chemical reaction. It eliminates emissions and organic wastes and obviates expensive catalysts like palladium. It also allows us to scale our reactors to the desired size instead of the huge sizes typically required by high-temperature thermal processes. We've done a laboratory-scale production demonstration showing over 99% efficiency in both aqueous electrochemistry and hydrogen atom transfer, and producing high-purity peroxide solutions. We've also run a preliminary techno-economic analysis, or TEA for short, that suggests we can achieve a break-even price approximately 50% of the current market price. In the last week, we've engaged Berk Techno-Economics to perform a professional TEA on this technology. The predicted savings are mainly driven by lower energy costs. The intuition for the energy savings is the same as the reason it's cheaper to heat a home with an electric heat pump than by burning natural gas. Much less energy is wasted in electrical processes compared to thermal processes. Harvard has a process patent pending on this technology and a strong portfolio of related composition of matter patents on the electrochemically active quinones. Adiabatic Materials is in exclusive discussions to license this technology from the Harvard Office of Technology Development, and we have a draft agreement in legal review right now. We are currently pursuing additional research to investigate ways to improve the efficiency of this process and generalize it to epoxides and caprolactam. We are seeking seed-stage funding to build a prototype device capable of continuous operation. This will increase our technology readiness level from TRL 4 to 5 and allow us to complete a rigorous TEA, which will in turn enable us to raise additional capital for a pilot-scale facility. In addition to these applications in commodity chemicals, we are only now beginning to investigate commercial applications of Richard's patent-pending nitro-reduction technology. The associated patent is part of the IP portfolio to be licensed from OTD. Early commercial development plans include synthesizing currently inaccessible novel materials for pharmaceutical clients and designing efficient continuous flow processes for drug production that combine traditional thermochemistry, electrochemistry, and interfacial transfer processes.